In this video, we're going to talk about intermolecular interactions. Intermolecular interactions are interactions that occur between different molecules. You may also be familiar with the term intramolecular. Intramolecular stands for within the same molecule. It's important for us to understand intermolecular interactions because this is going to help us to understand a lot of concepts in organic chemistry. For example, melting points and boiling points. Melting points and boiling points increase as intermolecular interactions increase. So if we understand those intermolecular interactions, we can predict these increases. Additionally, compounds with similar intermolecular interactions will be soluble, so this helps us to predict solubility. There are four main types of intermolecular interactions. The first and strongest are ion-ion interactions. Ion-ion interactions are attractions between positively and negatively charged ions. For example, sodium chloride has a positive charge on the sodium and a negative charge on the chlorine. That interaction is considered to be an ion-ion interaction. Next on the list is hydrogen bonding. Hydrogen bonding is typically the next strongest after ion-ion interactions. Hydrogen bonding is an attraction between a lone pair and a hydrogen. And very specifically, that lone pair must be on an O, N, or F, and the hydrogen must be on an O, N, or F. We'll look at several examples of hydrogen bonding on the next few slides. The next type of intermolecular interaction is dipole-dipole interactions. This has to do with the overall molecular dipole moment. In molecular dipole moments, you'll notice that one end of the atom is positively charged and another is negatively charged. And that attraction between the positive end of one molecule and the negative end of another is a dipole-dipole interaction. Next, we have induced dipole interactions. These are also commonly referred to as van der Waals interactions or London dispersion forces. This refers to an attraction between nonpolar compounds. And this is just caused by brief dipoles that are formed as the electrons are moving around. Let's take a closer look at hydrogen bonding. In hydrogen bonding, we're looking at the attraction between a lone pair on an oxygen, nitrogen, or fluorine, and it's interacting with a hydrogen that's attached to an oxygen, nitrogen, or fluorine. In this first example here, on the left, you can see the lone pair that's on an oxygen interacting with the hydrogen that's attached to an oxygen. This is a hydrogen bond, and the hydrogen bond is typically represented by this dotted line. You'll see the terms here, hydrogen bond acceptor, which is referring to the atom that has the lone pair, and hydrogen bond donor, referring to the atom that has the hydrogen. In this interaction, the hydrogen has a delta plus, or a partial positive charge, and the atom that the lone pair is on has the delta minus, or the partially negative charge. Some molecules have the ability to form different types of hydrogen bonds. For example, in this molecule here, you can see the hydrogen bond donor right here, and the acceptor over here. The acceptor in this top case is the OH of the carboxylic acid. However, in the bottom case, it's the carbonyl group of the carboxylic acid. Now, they both can't form a hydrogen bond at the same time, but either one is perfectly acceptable. Hydrogen bonding is extremely important because this is literally what holds your DNA together. In this image of the DNA double helix, you can see two strands of DNA. Here comes one up this way, and here comes the other way. In the middle, the base pairs are held together by hydrogen bonds. You can see one example here. In this case, two hydrogen bonds are holding these base pairs together. The hydrogen bonds here are represented with the red dots. Make sure never to show a hydrogen bond with a solid line because it's not technically a covalent bond. It's just an intermolecular interaction. That's why we use those dotted lines to show the hydrogen bonds. This is a nice visual to help you understand dipole-dipole interactions. In this case, we have an ether. Here's the ether drawn out here. The oxygen is in red, and the carbons are in black here. The negative end, or the delta minus, is up here, and the positive end, or the delta plus, is down here. So the positive end of one ether is attracted to the negative end of another ether. This attraction is a dipole-dipole interaction. Induced dipole-induced dipole interactions are similar, but the fact is these occur in nonpolar molecules. So for example, propane here, which I'll draw out, is just a 3-carbon chain. It doesn't have a negative end or a positive end, and this is what it looks like overall. However, as the electrons move around the molecule, sometimes you get a little bit of a negative end. And on the off chance that that happens to another propane molecule, then you very briefly end up with a positive end on one and a negative end on the other. They attract briefly, but only for a moment, because very quickly those electrons will move around and go back to this first state. Now we're going to apply these intermolecular interactions that we've learned about to understanding melting points, boiling points, and solubility.